together. Welcome everybody. We've covered a lot of what INL does, but it's all been like this big, broad brush strokes of here's what we do and we're the nuclear lab, but there's so much more to it than that. A big part of what INL does is the clean energy portfolio and how to get that to work well with nuclear or coal or any base load. And I think what Porter's going to talk about today should really tie it all together, just how complete the lab is. And for all the engineering disciplines and even the computer science. I mean, we're home now to three supercomputers. Our newest one, Sawtooth, a year and a half ago, was 37th fastest in the world. Of course, the next day we started dropping, but the computer science part of things is a huge part of the lab with all the modeling and simulation that goes on. So with that, I'll let Porter talk about what he does, and it is some mighty cool stuff. So they're all yours, Porter.
Well, thank you. I'm going to minimize that a little bit so I don't get distracted if you're watching me do that. Like I said, I'm Porter Hill. I'm a senior electrical engineer here at the Idaho National Lab. Today, we'll talk a little bit about green energy, microgrids, resiliency, and how they all impact the power systems. It will be a fairly high level discussion. I hope to allow time towards the end to ask questions. If we want to get down into more of the details, then we're happy to dive into those as needed. I did give you one little brief slide of kind of me, so you kind of get to know me as we got to know you guys a little bit. I've been with the Idaho National Lab for about 14 years, focusing on renewable energy and grid systems integration. I support primarily military installations with the projects that we have, helping them become more resilient, helping them develop the strategies that will take them from maybe a grid or a diesel backup primarily driven resilient process to now incorporating some of the renewable energies and the advanced controls that microgrids are allowing us to use. And that is where my research is with the microgrid controls and with the distributed energy resources. I should have DERs, you'll see that, and that stands for distributed energy resources, and how they interact between them and the grid. Before here, I worked for Boeing for a couple of years, primarily in the transportable power systems, whether they were in aircraft or unmanned vehicles. So I dealt with mostly battery systems and some with flywheels and some with fuel cells, but primarily on the DC systems. And before that, I worked for a couple of years at Raytheon in the satellite systems integration and test department, where that was more in the sensory development, sensors that were on satellites, and more of a consumer of power than the production or use of power, where I kind of found myself in my career now. Graduated at Utah State back in '04, excuse me. So, well, I was not aware that this particular audience had been hearing and learning and developing more about the laboratory. So I threw in a few headed slides here in the beginning to kind of discuss and introduce the labs. But the Department of Energy has the national laboratory systems that they have. These are really set up to help with the research and development to address the Department of Energy's core mission in energy science, national security, and environmental stewardship. So and then this second kind of bullet, we really try to help bridge the gap between the academia-based research and the utility demand for a more mature product that they can use and sell and make a dollar on. And that gap between the two is really where the national labs have found a home. So we do have some that get into the real meat of the pure science, and then some that are more into the applied research. And I tend to migrate more over to the applied research arena, where the research that we do is to help take the advancements that we're doing in technology, specifically to green energy and microgrids, and help them be applied into applications and installations that need that extra development. INL is one of 17 national labs, and you can see where kind of the other ones are scattered about here on this graphic. And we are the only national lab that is from the Office of Nuclear Science and Technology. We are a multidiscipline or a multi-program national lab. So we have kind of three big tiers of our mission: nuclear science and technology, national homeland security, science and technology, environment, energy and environment, science and technology, and this bottom one, this energy and environment, science and technology, is where I reside, and where we kind of spend our time. Some of the statistics, I won't go over a lot of these where it's being recorded. You guys can hit pause and read all this, but kind of the big hit items is a couple things I wanted to point out is one, we're already 890 square miles of our complex. This is a little bit dated, but I think we're still just maybe a hair over this number of employees here at the lab. We do have 7 substations and 112 miles of high voltage transmission line. And that's really what allows us to do some of the research that we're going to be discussing today, and how this renewable energy and how these things kind of can get worked in and play with the grid as a whole. And again, some of these other statistics are helpful for the nuclear side of the house that we could dig into. So kind of, and that's kind of the overview, if you will. If we're going to kind of jump into the more of the meat of my presentation, there are many distributed generation sources. So not only just the wind and solar, hydro, whether it's run of the river or the dam systems that we have. Those are typically all spread out from each other, and we have to be able to control those. We have to be able to use those. And as more and more wind, you don't put wind where it's convenient. You put the wind where the wind is blowing. Same with solar. Your natural gas with your combustion based fuels, or diesels with those fuels, and we're starting to get into this production of hydrogen, and this idea of hydrogen, and that would be a different individual presenting on the research that INL is continuing to do in that hydrogen production, where it dovetails in really well with the nuclear waste heat to drive and produce a pure hydrogen based, so that you can use that in for different fuels and different things. We are working on and with some of the small modular or micro nuclear reactor folks to integrate in the coming years a micro reactor into a battery, solar, wind microgrid, and to see that all kind of come forward and come to full circle would be, honestly, it'd be a capstone to a career. Actually, I think that's would be just simply awesome. But you have battery storage, lithium ion batteries, flow batteries, advanced lead acid, and different chemistries of those batteries that are now, especially with the lithium ion battery based chemistries, are becoming more and more economical. And the advancements in the flow batteries are becoming more economical, makes them more viable for these types of environments and products. But there are a lot of potentials. There's a lot of potentials for these types of batteries or these types of battery and the storage to be used for more than just the exchange of electrons. Um, they help with frequency and voltage regulation, peak shaving, and we'll get into some of that peak shaving or demand response. They help with the congestion as you get more and more devices and more things come on, how they interact and how they can develop congestion and how that is. But then it also has this backup power and outage reduction management element to it, which really has two sides of the same coin in terms of the benefit of each other. The thermal storage, and I'll be honest, we're going to talk just briefly about it, but I am not an expert on thermal storage. Uh, Maybe this gentleman that said he was a mechanical going to electrical, you'd be able to help us with some of that. But we have seen and do know of some systems that are more to help us with the load management, and they'll use whether it's heating of water, cooling of water, making ice to help regulate and use that power, but then use the building temperature controls as well to help store and use that thermal. And then this all includes the energy efficiency measures and design. So as we take all of these, if you kind of think about it as tools in a toolbox, you take all these elements and all these tools, and you're trying to build the most efficient system that you can, and so all these become what you're wanting to help build, not just for cleaning or using energy to satisfy that energy to clean the environment or have a clean energy source, but also to protect and accomplish the mission. And that's where the resiliency and the microgrids kind of come into play. This is kind of a graph. This is coming from a Bloomberg report with some projections on where they think, as you can see here, how the projection in coal comes down, and then that is being consumed or compensated for by its reduction, but then the overall growth is needed. That is primarily coming in the wind and in the utility scale solar. You've got a little bit of growth in the small scale. That's homeowners or commercial size solar, and you do have a little bit of either the biomass and some of the offshore wind that is being researched now. That's also going to help. Here at the Idaho National Lab, we would like to see this red bar become a little bit wider in these areas. You do see that how it's going to start growing here with the SMRs, small modular reactors, and some of the micro reactors, but we'd like to see that take a little bit more of a market share in the future. But we'll see how technology goes. The nice thing about Bloomberg and some of these others that are third party is they're driven. They help drive by economics more than by the coolness of the science. So at the end of the day, when you hit the markets, the economics need to pencil out. Here's just kind of another graph looking more in terms of the percentages rather than that load growth system. So you can see here where we are here in 20. This is dated by a few years, but you can really see how as coal drops off and these fossil fuels drop off, it is really the wind and the solar that become the compensator for that. But the one thing that we've got to talk about, and we'll talk a little bit about the aspects and the pieces of solar and wind, is the volatility. You don't get much solar power in the middle of the night, and when the wind isn't blowing, you don't get much wind. And so how do you solve that problem? And so that's some of the research that we're trying to do with the batteries and the storage and those controls. kind of just a brief, I'll kind of touch on solar and wind and batteries just at a pretty high level. Most of this will be review or even stuff of what you know. And so the biggest takeaways I want you to take from this is we've got a good handle on a lot of these technologies, but how we apply them and how we use them is non-trivial, and how we move that forward is really the crux of the research and the work that we're doing. But solar PV or photovoltaic is simply taking the light energy and directly converting that to electricity. Also known as a solar cell or a module or string. All of those have words that we'll use or hear and see, but that is they all are taking light from the sun and using those photovoltaic cells and converting that to usable electricity. The simplest form, as we all know, is usually our everyday calculators that take that light, convert it. We can help us do some math problems. But then that grows into more complicated systems. As you can see here down on the right, that is an installation where we helped an Army base and the Army Corps of Engineers implement a 2 megawatt solar array into an Army base, and we're in the process of helping them now helping them with engineering to help them put in a microgrid, some of the advanced controls, and some battery storage to improve their overall resiliency of their system. PV represents one of the most promising means of maintaining our energy and our energy standards of living, and contribute to the global warming and pollution. And so it is green energy. Once they're built, all you need is the sun, and you're producing power. Though they do have the output is DC out of the direct current. I didn't get into a lot of that, at least at this stage, but it is DC current. So it has a voltage, and it needs to be converted from direct current to alternating current so that it can be placed on our grid. And there's a lot of aspects and controls to that. I apologize. I pulled this graph here that you're looking at from another slide deck, and I don't know, this is not mine. And so I don't know who to give credit to, but I liked the graphic. And so if you know where this is coming from, or know what its source is, then I'd love to know and be able to give them the credit that they deserve for making this. But we're all familiar maybe with the term duck curve. And I'm going to use my mouse a little bit and kind of drive through some of this so you can kind of explain what solar does and how it impacts the grid. So this bell curve is really what you would consider the solar production. This is a fairly high level of penetration, meaning the solar impact on the overall system is a fairly high level. And so as the solar comes up in the morning, and this the blue then represents kind of a typical demand curve, and so that demand curve says this is the power that I'm going to use. So you would liken this to maybe a residence, where I wake up in the morning and I start turning on my coffee pot. I might turn on the news and lights and kind of run everything, and then I'm headed to work. And so my load profile kind of takes a dive when I head off to work, and then as the kids come home from school and start microwaving their snacks, and we come home from work and eat and watch TV and then start shoving off at night and going to bed, that becomes a fairly typical residential looking curve. Now, if I put solar on and I have this curve, what the utility sees is this high peak demand right here, and then it's gone for a little while, and then I see a big spike here in the evening when the sun is going down, and the demand for the power is still high. And so this is kind of the tail and the belly of the duck, and then here's the head of the duck, and that's why they call it a duck curve. Um, and and then this would be what its base loading is. And so that is the impact of just solar onto a system, and that has some benefits. It also has some cons, and we'll talk about um, when you get into a microgrid and you get into storage, what you can do to help mitigate some of these spikes as well as some of the volatility. This is a really nice looking bell curve, which is non-typical. Um, Solar usually is a very noisy, in terms of the power output, is a very noisy signal because of clouding, because of one day is different from the next, and also by time of year. The sun isn't always at the best at high noon. So as we deal with that, how do I solve the problem of having this volatile energy resource, and how do I make that so that it's one, dependable, two, available, when that's not around, and what does that system start to look like? Here, so there's two graphs on wind. Trying to change gears here on wind. I like these two graphs because they kind of show. Now there are four types of wind turbines. Type 1, 2, 3, 4. This is we won't get into the different types. If we want to dive into the different types of wind turbines, and which ones we want or don't want. But this one it kind of shows the main functions of what that different turbine types would be. So I have a hub or a central place that's going to spin about the wind as that wind hits these blades, and then turns that wind turbine. It's going to turn the main shaft, and that shaft is going to spin or turn at the same rate that wind is turning these blades. That's not always the optimal speed to turn a generator. So they have a gearbox, and basically this is um, maybe akin to your transmission in your car, or something along those lines. That says, I'm going to take this rotational speed coming into C, and I'm going to take it and make it more of a consistent rotational speed coming on the other side of that gearbox, and using its gears and using those things so that I can produce a very consistent rotational shaft on this going into the generator. Then this generator is spinning and producing power through that the generation fields. This graph kind of is another profile, but it does show some of the different controls of how I pitch my blades so based on wind speed, I'm going to actually rotate that blade and how it picks up and does that picking up the wind, and then also this yaw controller, so I maintain my point into the wind to help us with that. And so but and that graph is coming from this location here that we pulled from. It doesn't show up very well on that. We'll talk a little bit about battery storage. Battery storage or battery energy storage system takes not just the battery, but then also its inverters and its other power electronics, charge controllers, and all those other elements, and brings them into a system so that I can control those electrons coming in and out of the battery. I can recharge both with generator and with wind or solar, whatever other generation sources I have on there. It eliminates the intermittency of the solar. So as we kind of talked briefly about the solar and the wind, how I only produce solar energy when the sun is shining and hitting the array, and same with wind. I only produce wind power when the wind is blowing by my turbine. Um, the battery can start to absorb some of those volatility issues and some of the on and offs and ups and downs that the solar and wind are problematic for. They also support the UPS functionality and the lifespan. So UPS, uninterruptible power supply. I'm terrible and inconsistent with my acronyms. A bit of an acronym soup in some of these that I did not define. So I will take a note to fix that for future presentations. Um, we have spent a lot of time trying to integrate in this kind of capability into like a shipping container based size footprint so that they can be one deployable, two they can be modularized and stacked and built for the message or for the design. And now with the current technology being as good as it is, we're getting a lot of these different parts and components to be COTS or commercial off the shelf devices. And you're able to build these systems using UL listed components. Um, this just kind of shows in terms of graphic. This is from a study that PNNL did that kind of shows the cost. Now these costs, at least for the lithium ion battery in the last couple of years, this has come down by quite a bit. But you can see the supercapacitor is less expensive on the capacitance basis, and they are very tolerant for the cycle pattern. So I can take a supercapacitor and I can charge it and discharge it on its full range, and I can do that for many cycles. You can see here a million cycles, and those and you won't see much degradation. The battery, on the other hand, is less expensive on the energy basis. As far as content or the energy content side, it is a bit more than for a kilowatt hour. It is more expensive for than the supercapacitor. Um, uh, for the energy. So here you've got two terms when you start talking about storage. You've got what it can produce in the kilowatts. That's how much power I can push out, and then I add an element of time, and it's for how long can I do it. And so the batteries are the cheapest when you start dealing with total energy power content for short durations, or that the supercapacitor and are reasonable. Or more, the ultra capacitors last for just short bursts. Uh, you're comparable on the round trip efficiency. You're all pretty good there. But your flywheel is more expensive on that. You do have a lot of cycles. You see here 200,000 cycles before you start to see any kind of degradation. But you are paying quite a bit of cost premium for that. So that just kind of gives you a feel for, again, what are you going to be using this storage for? What is its mission and what you're trying to accomplish becomes kind of the driver for what you're doing there. Now I'll talk a little bit about microgrids. What is a microgrid? And there is some confusion, or some microgrid becomes a very popular buzzword. And I would like everybody to kind of understand that a microgrid is integrated energy systems consisting of distributed generators, energy storage, and or flexible loads which can operate as a single autonomous grid, either in parallel or islanded from an upstream utility. So when I take my RV out and I go to the sand dunes or wherever I go, and I start my generator and it charges my batteries and I can use that is considered an island grid. That is something small. It's all compact. It's all housed inside its own little device, and I don't need anything exterior to help me make and do my stuff. Um, and then I have the utility. When I take my RV to the KOA and I plug it in, I'm pulling off a utility grid. Um, and but a microgrid would be able to take those same components, but now with control and then bring them together to where I could be on the grid on the island. I could be off on my I could be on the higher, bigger utility grid or on an island grid, and I can go back and forth, use it or not, and be able to maintain the power system and the security that I expect to have. Why is this important? Probably less important when I'm camping. If I'm without power, the kids don't get to watch their shows, which is part of the reason why we don't want to be out. You camp because you don't want to be in front of the TV, right? So, but it is really important for the energy security and the resiliency of the power supply. So the end customer that is concerned about their mission can have that power quality and the reliability that they need, and uh, and so as something that is critical to have power, then that becomes why it's important is because they want to always have it be on. Um, how can microgrids help? Again, we talk a little bit about this for that critical infrastructure, such as hospitals, bases, data centers, communication infrastructure during that upstream power outage. But with the green energy and the other assets that we're introducing, the wind and the solar battery storage, they have a function that functions when they're in a microgrid, allowing them to provide that energy security and resiliency. But they also have a grid tie or an on-grid function where I can peak shave, where I can do many other frequency response. I can do a lot of other things, provide the power from a green resource, and have that be something that's there, which in turn helps the economic basis for the investment, and allows you to, and some of the benefits there on that bottom page, and I'm paraphrasing some of this, to be able to optimally manage the distributed energy sources so that I have those resources available in both conditions, and they have a benefit in both, but they're available for that mission when that anomaly, abnormal operation system happens where I've got to disconnect myself from the grid. Here's kind of again, the different kind of buckets or kind of the components of what that microgrid would be. This is not talking about the control elements or the power electronics. Obviously, we're going to have inverters and both and different types of inverters, the grid forming good type inverters following. But really, this is kind of a one line that kind of shows, hey, I can have storage, I can have wind, I can have solar, I can have these micro turbines, and I can pull all of those in with these. Here's an inverter that's converting the DC into AC with a microgrid control piece. That all kind of flow into being able to be controlled by this central controller, and then interact with that grid. Hanging off of this with this other controls can be your natural gas, can be your diesel generators, can be nuclear for your base load.
Tyler, what's up?
Excuse me? Oh, okay.
I muted him. Sorry, he
Okay.
jumped off.
That's okay. And then you have your battery storage or your storage that could be battery or thermal storage that can help make up those components. So why do we want a microgrid? And I've kind of talked a lot about some of these different parts and pieces, but it allows you to have that more control over your energy supply, and it allows that energy security piece. So the reliability, availability, resilience improvements for more than just a base. Is you guys can kind of read this. An example would be your hospital where they have a UPS sitting on the wing that has the ICU, and then has a generator outside the building. And then as the power goes out, the UPS carries you for a minute or two while the generator is starting, and then the generator starts. And both those options are good, and they keep people alive, and that's why we invest and spend the money on doing that in the hospitals. But when the power is good, which is 99.9% of the time, that generator is doing nothing for you. I still do my maintenance on it. I still do my preventative maintenance and my checks monthly. I still top off the fuel and check the oil, and I still do all of those things. But again, 99.9% of the time, it isn't doing anything for me. Whereas if I can replace part of or one of those with a with solar or battery, I can be using that in 99.9% of the time. That then allows me to use that, but it also then becomes a non-fuel dependent system, right? I don't need to fill it with fuel if I don't have it. Now, in some scenarios, or a lot of scenarios that we use, what we end up doing is optimally sizing the different components, whether that's the batteries or the UPSs or the generators or any of those things, so that I maximize that benefit of having all those different tools in the toolbox, if you will. It also enables to more optimally run the gen sets. So in a lot of places where we have critical loads, we don't start one generator, we start two. In case the one has a problem, the other one will pick up the slack. And when I have a battery, then all my loads can be picked up by one of the generators or most of the generator. Then I can optimally load that, because I can be charging or discharging the battery to hit that sweet spot in the generator. But then I can also have that battery pick up any of those extra loads, so that I'm not running that second gen set, so I'm able to compensate for that spinning reserve requirement. And then it also helps with the green energy goals and energy supply that kind of drives this technology. Then to kind of circle back and look at this, here's the duck curve discussion again. So this is a different set of data, but again, it's a fairly high level of penetration of that solar. But kind of follow along with my cursor here. This curve on the top becomes the overall demand, what this system needs to look like. And now this is more of not a residential view or a residential look. This is more of a industrial, where people start showing up to work in the morning, and they're talking with their neighbor, and they're starting to drink their coffee and turn stuff on. And then here at noon, they're starting to turn on they're eating their lunch, and they're doing a few things, and then they're starting to peak here, finally getting their work done towards the end of the day, closing time, and then they're starting to shove off. So that is more of an industrial or commercial based view. Then here becomes my bell curve again with my solar production. But now I've entered, and then here's the duck curve. Here would be the duck curve if you didn't have the battery. But now when you introduce the battery, and that battery becomes part of the equation where I can absorb the solar, extra solar production during the peak solar production times, and then I can discharge the battery during the less solar dependent times, then you can see that my demand curve goes from being way up here near 100 to peaking out in the middle of the night at closer to about 70. So that's a 30%, if you call these percentages. It's a 30% reduction in that demand. That is, in many cases, that is a very important number. There's tens of thousands of dollars, depending on the system or whatever it is, that is saved just by reducing that demand charge. And so that's what we talk about when we say peak shaving or demand response or some of those things. But it's how I use this battery's charging and discharge capability to flatten that curve. But what you'll also know is that the base loading is more depictable. It's more predictable, and so my utility company sees less volatility. It doesn't see this big swell dip. I should have called this a dip. This big dip in the middle of the day, and then this big swell in the evening. So this becomes a more robust system, and I keep enough reserve in my battery so that if anything happened to the grid at this time, I'm able to compensate and react to that, which kind of drives us into this idea of resiliency. Resiliency is addressing the high impact events. These are different definitions of resiliency. Addressing high impact events and the consequence of which can be geographical or temporarily widespread. The ability to prepare for and mitigate major extreme events and disasters. Also the capability of individual and institutions, businesses, and systems to sustain and recover from chronic stress and acute disturbances. So really, and I'll show you another curve. This is the last curve before we get to questions, and we'll open this up to discuss just briefly about resiliency. And that is, and this is coming out of some of the research that has been done by a lot of folks here at INL in the resiliency arena, and it's kind of been adopted for this purpose. But there are 5 R's of resiliency. So recon, resist, respond, recover, and restore. And each one kind of has their own kind of pieces of how we do that. And so recon would be considered, I'm running, I haven't seen an event, and then how much of that event, or where are my vulnerabilities? It's really becoming smarter about your system and knowing where those vulnerabilities are. So in the power system, we might say, well, do I have inverters or switches or components that are in my power system that are susceptible to power, voltage sags or voltage swells that would cause them damage, or an outage. What would cause an outage? Different things that way. And then how will I resist? So you can kind of see the tolerance, if you will, of what this R value, or this resilient threshold, says. How much of a disturbance, an event that happens, how well can I respond or resist that? How can I do something ahead of that, or at the moment that happens, to lessen its impact? So the UPSs do that, right? They resist that impact of an outage by stepping in and providing that power. They only provide power for just a short period of time, before I need to respond. And that becomes what my reaction is or what my response to that outage is. And so you have to pick that threshold of what I'm okay with my system doing, and try to, if it's not good enough, so I'm not resilient enough towards the outage that I'm trying to mitigate against, I've got to find a way to get this red line up closer to the green line. And then I still need to respond. I need to start the generator. I need to kick in and transition from grid following to grid forming in my microgrid. And then I need to recover. I need to do whatever I need to find and figure out what needs to happen to mitigate or to eliminate whatever that event was. And then once I've recovered from it, I've eliminated that issue, then I can restore and get back to normal. And that becomes a way of helping us understand our system well enough to become more and more resilient, and help us measure ourselves, if you will, in those systems that we have. And the crux of, and this is how I'll close and open it up to questions, but that is the crux of why we want to use microgrids. One, it has a dual purpose. I can use solar and battery and everything for a grid tied function that makes sense economically as well as functionally. Those same devices allow me to go off the grid in an islanded mode, and they provide that resiliency, that power quality, and that other aspects to allow me to island and maintain mission readiness in that event. And because they happen to have in both arenas, that allows them to maximize those drivers and make both cases more economical and more beneficial to those end users. With that, I thank you for your time. I have this one last slide that's got my contact information and a few of the key other players that I know and work with close in our group. But certainly happy to entertain any discussion, any further details or questions that anybody might have. And with that, I'll turn it back over to Don. Thank you.
Does anybody have any questions?
Yeah, I do have a question.
Go ahead.
Can we go back to the slide outlining the cost of each of the storage systems, battery versus supercapacitors versus? Yeah. Do you guys have ultra capacitors that you experiment with at INL?
Yes. So just this last week, a group took a supercapacitor over to the municipal here in Idaho Falls Power, and used that to help them black start and look at some of their turbine for their run of the river hydro that they've got there along the Snake River. That was just last week.
Really cool. Okay. Is there kind of a limit there for the amount of storage you can get out of a super ultra capacitor system versus a lithium ion battery?
Yeah, great question. I think if I answer it, hopefully satisfactory. So a supercapacitor is really kind of targeting that very fast, short duration power need. So I have a supercapacitor, and I need to dump all of its power content in a very short period of time. So my energy content, as you can see here, and it's reflected in the costs, right? So it's cheapest in the dollar per kilowatt. So that's how much power I can give you at any one given time. How long I can give you that is the cost per kilowatt hour. And it's not long before your batteries become a lot better of a solution if you need power for beyond just a couple of minutes. So a supercapacitor will help in the minutes, whereas a battery is going to be the better solution for that longer duration, or even into the many minutes or tens of minutes or hours type of deal. You would, and again, kind of going into some of this duck curve mitigation. This is not a solution for a supercapacitor. What you would ideally look at potentially would be to pair a supercapacitor to solve your very short term, your frequency response, your voltage regulation, and some of those that are kind of a quick mitigation pieces. And then you dovetail that with a a battery that allows you that more long term solution or energy content, that more energy. So anyway, I hope that answers your question there.
Yeah, absolutely. So from like a resiliency standpoint, you could, as you made the example from with the battery paired with the generator, you could have an ultracapacitor paired with a battery paired with a generator for your most resilient but likely most expensive solution.
Yeah. So yeah, depending on what so that's where I think you all are good answers. It's like the keys on a piano. Every key is the right key at any one given time, and every key is the wrong key at any other given time to be able to make the system or make the music go. And so a supercapacitor, ultracapacitor, flywheel, lithium-ion, thermal storage, all of those things by themselves have elements that are good and need to be used at any given time that are the wrong answer in another case or another environment. And so the balance is understanding your requirements and understanding what the system is and the mission, so that you can build, again, all these tools in your toolbox to be able to build that system with resiliency in mind, with the economics in mind, so that the solution becomes the most robust that you can do with the given system.
Very cool. Okay, thank you.
Sure, good question. Thank you.
We have another question from the chat, and feel free to look at yourself. However, I'm happy to read it. Is there a difference between the vulnerability, for instance, hacking over the internet, of the systems running on older power, such as coal sources, versus these new clean energy systems?
Yeah, great question. And as systems become more and more computer based, the risk of being vulnerable to a cyber hack or cybersecurity vulnerability becomes more and more. So your old strictly just mechanical devices that had no computers in them, the security was primarily physical. As long as somebody was sitting at the gate and not letting the bad guy in, then you were okay. But as soon as you now start touching the cloud, you start doing any kind of more advanced computer-based electronics that then has an internet touch to it, then you're now vulnerable to that, which is a different piece of that resiliency. How resilient am I as a system to a cyber attack? Do I open up enough ports to do my job? But when I open up too many ports, now that opens up the back door for somebody to find a way in as a hacker. That said, going back to the very kind of introduction, this National Homeland Security and Science and Technology, which is a huge development, or this huge part of the Idaho National Lab, there is a large constituents that is focused on just that type of analysis and vulnerability sets. And so, although not necessarily my focus or my bailiwick, certainly a concern, and certainly there, and that we address as well when we do this. It's a risk management framework. RMF is what the military Army uses that we follow. It used to be, I can't remember what it used to be. Darn it, I used to know, but that's what it uses now.
If I can just add a little to that for you.
Yeah, thank
Well,
you.
I think one of the things the lab has seen with quite a bit of the testing that we've been doing, we've shown that there are vulnerabilities in power grids and a lot of different things. But when it comes to the utilities or whoever it is actually addressing those vulnerabilities, one of the drawbacks is, as Porter has talked about, the economics have a huge impact on the decision. And some utilities have said, well, that hasn't happened yet.
Right.
And we've got stockholders. They don't want us to dump all this money into fixing something that hasn't happened. And that's where the big holes get left quite often, are just, well, it hasn't happened yet. We're not going to spend money on it yet. And y'all may remember, was it 2 weeks ago, 4 weeks ago, we had Ethan Huffman from the National Security Group said one of the big pushes now is for the cyber informed engineering. So when you're putting these systems together, like a microgrid, consider the cyber protection while you're building it, not as a bolt on afterwards, and just try to avoid, prevent as much as you can in the design instead of later on.
And that becomes, and sorry, I kind of blew by that because I was going to pick that up. That becomes this piece of that resiliency. This is called the Dyer curve, but and that's what this, that's that acronym. But that really becomes that recon. As I develop, as I make my system, as I do that, if I take into consideration those vulnerabilities, what that event might look at, whether that's a cyber, physical, whatever kind of risk, then I can build that in. And if I do that on the front end, it is certainly cheaper to do that on the front end.
Any other questions that anybody may have? I put in the chat box a link for any feedback or anything, if you would quickly do something like that or go to the link. But otherwise, Don, if there's no more questions, then Don, would you like to do a quick closing for us, or?
I think the biggest thing is good luck with finals. As my dad likes to say, I've got credit in that course. I don't have to do them ever again. So everybody enjoy your finals, and we look forward to picking this up again next fall. And maybe by then we might even be able to send speakers to Laramie, which would be really cool. But I'm not holding my breath yet.
I'm looking forward to when we can bring students to Idaho National Lab and be able to spend time going through some of this stuff there too. So,
even better. Yep.
Yeah.
Yeah, come and see us. We'll take you through our microgrid.
Yeah. Well, Porter, thank you so much for your time. Don, for yours. Sophia, for helping us organize everything. We really, really appreciate it. This has been very informative.
Thank you.
This session as well as all of them.
Very good. Glad to hear that.
Yeah.
All
Well,
right.
if there's no parting words, then I guess we're out of here.
I'm good. Enjoy finals and have a good summer.
All right.
Thank you.
Thank you, students, for participating. We appreciate it.
Indeed.